As you have already understood, it's a science that studies mathematical methods that allow you to display your information in a way that will ensure its confidentiality, integrity, and even availability when it's transmitted. Claude Shannon brought great influence and development in cryptography. In his works, he summarized all the accumulated experience in the development of ciphers. It turned out that even in very complex ciphers as typical components, it's possible to single out, at least theoretically, such simple ciphers as substitution cipher, transposition cipher, or their combinations. The substitution cipher is the simplest, most popular cipher. Typical example is the scissor cipher. As can be seen from the name, the substitution cipher performs conversion of the replacement of letters or other parts of plain text into similar parts of the ciphertext. It's easy to give a mathematical description of the substitution cipher. Let's denote X as characters of the plain text and Y as characters of the ciphertext. Then X will be replaced by an element Y with a certain rule, where a special role, as elsewhere, plays the key. The key is an abstraction that denotes a certain length or set of elements. This key helps to change our plain text beyond recognition. For example, with our rules, our plain text is displayed as Y. Well, here's some basic math. What I just explained to you, it's customary to write as one-to-one mapping of X to Y. Then the substitution cipher works like this. Plain text from X sub 1 to X sub n is converted to the encrypted text from G of X sub 1 to G of X sub n. But why does cryptography always change? Why the ciphers get hacked all the time? The problem usually lies in the key. In cryptography, there is such a thing as cryptographically strong cipher. Any such cipher is similar to the so-called one-time pad, in the sense that the secret key must be completely random, use it only once, and its length must not be less than the length of the plain text. Let's look at the simplest example of the implementation of cryptographically strong cipher, where Y sub I is equal to X sub I XOR K sub I, where I is equal from 1 to n. Here, our X sub n is the plain text, and Y sub n is encrypted text. And the last one, K sub n, is the key. This cipher performs bitwise addition of n-bit plain text and n-bit key. Now I'm going to deviate a little from the topic specifically for those who do not know what XOR is. The exclusive OR symbol means a binary Boolean operator that takes the true value only when one and only one of the incoming values is true, that is equal to 0 or 1. But if both input values are the same, then it takes the false. Let's consider the example where x is equal to 1, 0, 1 and y is equal to 0, 1, 1. Then in the operation XOR we get the result. 1 XOR 0 is 1, 0 XOR 1 is 1, but when 1 XOR 1 we get 0. So our result is 1, 1, 0. The symbol of XOR is very common and is denoted as this. Also, it has the following features. First, you can imply XOR in any order. For example, A XOR parenthesis B XOR C is the same as parenthesis A XOR B and XOR C. Next, you can flip the operands around. A XOR B equal to B XOR A. Any bit XOR itself is 0. I'll explain. A XOR A is equal to 0. If A equal to 0, then we get 0 XOR 0 is equal to 0. And if A equal to 1, then 1 XOR 1 is also equal to 0. And the last one, any bit XOR 0 is that bit again. A XOR 0 is equal to A. If A equal to 0, then 0 XOR 0 is equal to 0. But there is a difference. If A equal to 1, then 1 XOR 0 is equal to 1. Now back to our cryptographically strong cipher. We emphasize that for cryptographic strength is essential each of the following requirements for one-time pad. First, complete randomness of key. This in particular means that the key cannot be produced by any deterministic device. Second, equality of key length and length of plain text. And the last one is single-use key. In case of violation of at least one of these conditions, the cipher ceases to be cryptographically strong, and there are fundamental opportunities for its deciphering, even if they can be difficult to implement. But it turns out that these conditions make cryptographically strong cipher very expensive and impractical. Before using such ciphers, we must provide all participants with a sufficient stock of random keys and exclude the possibility of their reuse. And this is extremely difficult and expensive to do. That's why even Caesar cipher can be cryptographically strong. Today, hacking attempts typically are made on a non-mathematical part of the cipher. They are aimed at software or hardware bases. If the mathematical method of the cipher base guarantees its durability, then it's impossible to crack it. But that's the problem. It's impossible to provide this mathematical strength for a number of reasons. In addition, developers make mistakes in the code or the exchange of keys, which are the cause of cracking the cipher. So, for now, cryptographically strong ciphers are used in the government, where encryption algorithms are in the strictly confidential, just in case. So, in the 21st century, we protect our money in the bank through mechanisms that could be cracked in theory. The only question is, will there be enough of the enemy forces, means and time for the development and implementation of the algorithms? This is usually conveyed as, adversary with unlimited resources can crack any cryptographically strong cipher. So, how should a legitimate user act in this situation? How to choose a cipher? The best thing, of course, would be to prove that no opponent can crack the chosen cipher in, let's say, 10 years, and thus get a theoretical evaluation of the strength. Unfortunately, mathematical theory does not yet give the necessary theorems. They relate to the unsolved problem of lower estimates of computational complexity of problems. Therefore, in practice, it's necessary to use an alternative approach to obtain so-called practical estimates of strengths. To do this, you need to do the following: to understand and clearly formulate from what enemy we are going to protect the information. It's necessary to understand what the enemy knows or will be able to learn about the cipher. as well as what forces and means he can use to crack it. Eventually become the position of the enemy and try to attack the cipher from his position. To develop various algorithms for cracking the cipher, it's necessary to maximize the simulation of forces, means, and capabilities of the enemy. The best of the developed algorithms used for practical evaluation of the strength of the cipher. Here it's useful to mention two simple methods of dissecting the cipher. Random guessing of the key. It works with a small probability but has a small complexity. And search of all keys in a row until finding the true one. It works always, but has a very large complexity. Note also that it's not always necessary to attack the key. For some ciphers, you can immediately, even without knowing the key, restore the plain text from the encrypted. Mathematical methods used in cryptography cannot be successfully mastered without knowledge of algebraic structures such as groups, rings, and fields. Haha, not this one. But we will talk about them in more detail in another lesson. In order to understand the operation of cryptographic systems, it's necessary to understand some mathematical bases. These bases consist of the foundations of the theory of numbers and the theory of quadratic residue, but it's not as difficult as it seems. Don't panic, of course, it seems much more terrible than it actually looks. A finite field or Galois field, called a finite arbitrary set of elements with given between them operations of addition, multiplication, and division. These operations must have the following properties. For any A and B, where A and B is an element of Galois field, A plus B is also an element of GF parenthesis Q. For any A and B is an element of GF parenthesis Q, A multiply B is an element of GF parenthesis Q. A plus B is equal to B plus A. A multiply B is also equal to B multiply A. Parenthesis A plus B plus C is equal to A plus parenthesis B plus C, and it's equal to A plus B plus C. A multiply parenthesis B plus C is equal to A multiply B plus A multiply C. For some element 0, where 0 is an element of GF parenthesis Q, A plus 0 is equal to A, and for any A is an element of GF parenthesis Q. For some element minus A is an element of GF parenthesis Q, such that A plus parenthesis minus A is equal to 0, and any A is an element of GF parenthesis Q. Also, for some element E is an element of GF parenthesis Q, A multiply E is equal to A, and any A is an element of GF parenthesis Q. And the last one, for any A is an element of GF parenthesis Q, where A not a 0, for some A to the minus 1 power, such that A multiply A to the minus 1 power is equal to E. So, it's not hard, isn't it? In reality, it works as follows. For example, we have our field denoted by the letter P and it equal to 5. Then, all the operations we are dealing with are made with the numbers 0, 1, 2, 3, and 4. If our P is equal to 7, then we will work with 0, 1, 2, 3, 4, 5, and 6. It's simple. If we need to add or multiply field, then it will look like this. As an example, I took GF parenthesis 2, which consists from 0 and 1. In this way, you can better understand this thing. So, let's first add our numbers. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is also equal to 1. But when you add 1 and 1, then you get 0. Next, multiply. 0 multiplied 0 is equal to 0. 0 multiplied 1 is also equal to 0. And also we get 0 when 1 multiplied to 0. But when we multiply 1 and 1, then we get 1. Let's consider our previous example where p is equal to 5. First, we should build these two tables. In the first table, we will add the values. So, 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. And 0 plus 2 is equal to 2. But when we add 3 to 3, we get 1. Why did this happen? This is because when filling in our values, we need to subtract modulo p. In our case, p is equal to 5, so we get modulo 5. If our p is equal to 7, then we get modulo 7. Let's consider second table. 0 multiplied 0 is equal to 0. And when we multiply 2 and 4, we get 8. 8 subtract modulo 5 is equal to 3. As you can see, the math in cryptography is pretty simple. It's only important to understand the basic concepts and formulas. But most importantly, you can find a huge number of examples that will help you learn the material. So, let's get into this math a bit. The most basic thing we faced in cryptography is a set. In mathematics, this is the most common concept. Here's an example. This is a set of different elements. It can be any elements. All these things are elements of the set. They are usually written in braces. For some especially important sets of numbers, standard notations are adopted which should be followed. Thus, the letters N, Z, Q, R denote respectively the natural numbers, the integers, the rational numbers, and the real numbers. If you see this symbol, it means that A is an element of the set of S. If A is not an element of S, then the record corresponds to this kind. If some set included in another set, it looks like this. Then we get that S is subset of T. So, if X is an element of S, it means that any X is an element of T. Sets are equal only if they have the same elements. So, S is equal T only if S is subset of T, and T is subset of S. And now a little pun. An empty set is a set that does not contain any element, is by definition a subset of any set. The intersection of two sets looks in this way. So, we get that X is an element of S, and X is an element of T. In this case, the intersection of sets occurs with elements X and B. And finally, this is their union. The set S combined with set T. If X is an element of S or X is an element of T, they can combine and create a new set. So, why you need all of this? In cryptography, you are dealing with a set of elements of open and closed text. It's not necessary that it will be the text, but in cryptography, it's accepted to designate any open elements as plain text and any closed as ciphertext. And when you convert plain text to ciphertext and vice versa, you're working with a different set of elements. When you do cryptanalysis, you work with a set of elements too. And these elements interact with each other. Their mathematical properties must ensure the reliability of the cipher, and these sets are formed by similar methods. Therefore, the set is one of the basic mathematical concepts in cryptography. The next concept is the relation that associates each element, or in other words, function. For example, we have x and y. The function f with element x and element y maps each element where x is an element of x and element f of x where f of x is an element of y. Symbolically, the map is written such like that, where f such that x maps to y. Simply, the set x has a function f that takes values from the set y. This is how the cipher works. For example, there is a function that works with the plaintext elements and takes the values of the ciphertext elements. That's it, so simple. The next element is the binary relations. For any two sets x and y, any subset of big O is called a binary relation between x and y, or simply on x if x is equal to y. A binary relation on x is called an equivalence relation if all conditions are met with next requirements. Reflexive, it's when x similar to x. Symmetric, if x similar to x1, then x1 also similar to x. And transitive, if x similar to x1 and x1 similar to x2, then x2 is similar to x. So, what is a binary relation? Let me give you a more clear example. Let's say you are a student and you are writing a math test. You have solved the task number 5. This means that you and task number 5 is in some relations. These relations may or may not be. As a result, we have two sets, for example B, all students of the group where the test was, and P, all the tasks that were solved on the test. A binary relations is a relations between sets that indicates who and what was able to solve on the test. So, in cryptography, with the help of binary relations, we can decide which elements of the set are in the relations with other sets or their elements. Next, consider the divisor. An integer s is called a divisor or multiplier of an integer n if n is equal to s multiply t, for some t is an element of z. In turn, n is called a multiple of s. The divisibility of n by s is denoted by this symbol. Very often in cryptography we deal with binary algebraic operations. For example, we have a set of elements x. A binary algebraic operation on x, or the law of composition, is called an arbitrary but fixed mapping of this definition of the Cartesian square, where x in the second power is equal to x multiply x in x. Thus, any ordered pair A and B, which elements of x, is put in correspondence with a certain element, tau parenthesis A and B, of the same set X. Sometimes, instead of tau parenthesis A and B, they write A, tau B, and even more, often the binary operation on X is denoted by some special symbol, such like that. We can specify many different operations on X. If you want to highlight one of them, use brackets, and say that this operation defines an algebraic structure on X, or that this is an algebraic system. It can be visualized as in the set of integers z, in addition to the natural operations addition and multiplication, it's easy to specify the resulting by using plus or minus, and even multiply for derivatives operations. In this way, we come to different algebraic structures. This is just a small example of how much mathematics is in cryptography, but having dealt with it, you will understand that it's not so terrible. You just need to take the time for this. The mathematical basis allows us to work with algorithms. The algorithm is a specific computational process which allows to process the input data into the output result for a certain number of steps. In cryptography, we distinguish between deterministic and randomized algorithms. The deterministic algorithm always acts on the same scheme and is guaranteed to solve the problem, or in another case it does not give any answer. The randomized algorithm uses a random number generator and does not guarantee an exact answer. Let's take a look at each example. Let's say the deterministic algorithm is a fraction division algorithm. For example, b, c, and d is not equal to 0. Then a over b divided by c over d is equal to a multiply d over b multiply c. Otherwise, there is no other answer. The randomized algorithms give the answer to the question, the number p is simple or not. In this case, you need to generate a random number a, where a is less or equal to, and a is less or equal p minus 2. Then we can check the equality a in the power p minus 1 is equal to 1 modulo p. That is all we need to understand whether the number p of length 100 decimal places is simple. We need to sort the number a from 2 to p minus 2. In general, randomized algorithms are no less effective than deterministic ones. For example, if a random number generator always produces a set of the same numbers, possibly dependent on the input, then the randomized algorithms becomes deterministic. In modern logic, along with the concept of algorithms, there is the same fundamental concept as calculus. Calculus is a way of creating a set by specifying the source's elements and rules for deriving new elements from the source or already built one. An excellent example is chess. When you move the chess piece, the next steps depend only on the position of the pieces on chess and the position of the figure itself, already knowing how this figure moves. Calculus is a list of rules. Unlike the algorithms, these rules do not prescribe but allow to move from one structural object to another. The algorithm defines an algorithmic process, while the calculus process sets the generating process, and this process is divided into separate steps, each of which consists in obtaining a new object from the already obtained by the beginning of this step. The objects to which the rule applies are called its parcels. In this case, the same rule that we apply to the same parcel can give different results. The object which is obtained in the process of calculation is called permissible. For example, if the object y is obtained from a permissible object A using the permissive rule, then it's permissible. This is a common logic that functions under cryptographic operations on your computer. Every calculus works with elements of a certain set called the working environment of calculus. All states of the computational process lie in this set. The work of the calculus process lies in the formation of new acceptable elements of the working environment. For example, you need to encrypt the text using an algorithm with 128-bit key. Algorithms and calculus are rigidly coupled. For each calculus generating a pair x and y, there is an algorithm for which x is an input and y is an output. But what determines the quality of the algorithms? Its complexity. To determine the complexity of the algorithms, we can associate each problem with a certain number called its size, which would express the measure of the number of input data. For example, for the multiplication problem of numbers, the size can be the length of the largest of the factor. For multiplying square matrix, the number of rows of the matrix. Time displays the number of elementary operations of the computational model, and the same time spent by an algorithm as a function of the size of the problem is called time computational complexity, or simply the complexity of this algorithm. The value of this complexity with unlimited deviation of the problem size is called asymptotic time complexity. The complexity of randomized algorithms can be compared if the probabilities of getting the correct result are the same. If the algorithm requires the storage of some data obtained during its operation, the amount of memory required for the operation of the algorithm in the solution of the problem of this size, called the capacitive complexity of the algorithm. In practice, the complexity of the algorithm is estimated using the asymptotic complexity and denoted by this symbol. If the algorithm can solve the problem in time no more than Sn, where S remains a zero-bounded value with increasing number n, then it's said that the asymptotic computational complexity of the algorithm is big O parenthesis n. As a rule, in practice, it's required that the algorithm can solve not a specific problem, but a wide class of these problems. These requirements come out of the fact that it's better to get the most overall result with the minimum of costs. This class of particular problems will be called a math task or simply a task. Let's say an algorithm A can solve a class of T problem if it solves every particular problem from class T. Then this algorithm is universal. So, why do you need all of this? When you develop an encryption algorithm, it's very important to consider the fact that it will have complexity. When you generate a set of random numbers by a certain rule, it's very important that these numbers do not intersect with each other. This will help you to avoid brute force attacks. If you're replacing plain text with ciphertext, it's important that the same characters are not repeated. This will help to protect against cryptanalysis. When you encrypt some data, it's important that the algorithm is very fast and efficient to cope with its task. Otherwise, how will you transmit this information through the internet? Who needs an algorithm that encrypts and decrypts a small amount of data for a few days? These are only basic examples of what mathematical principles are used in cryptography. But as you can see, there is nothing complicated. The whole task of cryptography is to create a random key and generate random elements of the ciphertext, which can be replaced by the elements of plain text, thereby encrypting the message. In the case of the substitution cipher, in the shortest possible time, with the greatest efficiency at the same time. Next, we'll talk about random numbers and the fields, rings, and groups.